Light travels at 186,000 miles per second, yet it still takes more than 4 years to reach Alpha Centauri, our nearest stellar companion. To traverse the Milky Way at light speed would consume 100,000 years of continuous flight. Humanity faces imprisonment within an invisible cage constructed from the fundamental laws of nature. However, what if these seemingly unbreakable laws contain exploitable loopholes? Scientists have developed theoretical frameworks suggesting spacecraft could achieve velocities exceeding light by a factor of 10, transforming missions requiring centuries into expeditions lasting mere decades. You're about to discover laboratory experiments producing actual warp bubble signatures, methods for detecting alien spacecraft through gravitational wave analysis, and energy calculations that have plummeted from utterly impossible to merely extraordinarily challenging. If this breakthrough excites you, show your support and subscribe, because we're entering territory where science fiction becomes scientific possibility. Let's dive in. The Cosmic Speed Trap. The Parker Solar Probe represents humanity's fastest spacecraft, achieving velocities approaching 430,000 miles per hour around the Sun. This achievement sounds remarkable until you calculate the journey time to Proxima Centauri. Approximately 6,700 years. Your voyage would commence during the Bronze Age and conclude in our distant future. Conventional rockets have trapped us in a velocity prison from which chemical propulsion cannot liberate us. Photons themselves travel at 670 million miles per hour, yet still require 4.24 years to span the void between Earth and our nearest stellar neighbour. Our galaxy stretches 100,000 light-years from edge to edge. Simple arithmetic reveals that crossing this distance becomes an odyssey spanning multiple human civilizations. Each distant sun you observe twinkling against the night represents a target utterly beyond reach using contemporary propulsion systems within any human lifespan. The Voyager spacecraft, launched during 1977, have now journeyed beyond 15 billion miles from their origin point. These probes have travelled for nearly 5 decades, yet they haven't completely escaped our solar system's gravitational dominion. The stellar realm remains frustratingly, impossibly distant. We exist as cosmic toddlers attempting to crawl when our survival demands we learn to run. Here's the unvarnished reality. Space doesn't simply possess enormity. It actively ridicules human ambition. The gulfs separating stars span such incomprehensible distances that even achieving 99% of light velocity would transform interstellar expeditions into multi-generational undertakings. Your great-great-great-grandchildren might witness the destination you selected. Every propulsion mechanism we've engineered operates on identical fundamental principles. Expel mass from the rear to generate forward momentum. Chemical rockets combust propellant. Ion thrusters eject charged particles. Nuclear engines exhaust superheated plasma. Each system obeys classical mechanics, and each crawls relative to the cosmic distances demanding traverse. This challenge earns the designation tyranny of the rocket equation among aerospace engineers. Increasing fuel capacity makes your spacecraft heavier. Greater mass demands additional fuel. The situation spirals into catastrophe, where fuel tanks must dwarf entire metropolitan areas just to attain fractional light speed velocities. Enhanced thrust merely compounds the weight penalty. We've dispatched robotic explorers to Mars, landed sophisticated rovers on distant moons, and captured photographic evidence from the observable universe's boundary. Yet we remain confined to our immediate cosmic vicinity, gazing at barriers we cannot surmount. The closest potentially habitable exoplanet orbits just 4 light-years distant. Current propulsion technology would require 80,000 years of continuous operation to arrive there. Something must fundamentally change. The cosmos contains billions upon billions of potentially life-supporting worlds, yet humanity can barely reach the nearest rocky body in our immediate neighbourhood. But what physical principle chains us to this agonizingly slow reality? The answer emerges from equations formulated by one man over a century past, Einstein's prison. Albert Einstein published his special relativity theory in 1905, and through those equations, he constructed an invisible barrier around human civilization. His mathematical framework revealed something shocking. Nothing possessing mass can achieve or surpass light velocity, ever. The universe itself enforces this restriction through spacetime's fundamental structure. The reasoning appears deceptively straightforward. As objects accelerate toward light speed, their mass increases, not incrementally, but exponentially. A spacecraft approaching light velocity would accumulate mass exceeding entire galaxy clusters. Accelerating it just 1 mile per hour faster would demand energy increases of astronomical magnitude. This generates a cosmic paradox. You require energy to accelerate mass, but acceleration increases that mass, demanding additional energy, which further increases mass. The cycle spirals toward infinity, precisely at the threshold where you would breach the light-speed barrier. The universe essentially declares, approach this limit asymptotically, but never cross it. Einstein designated this a universal velocity ceiling. For over 100 years, his mathematics have withstood every experimental challenge. Particle accelerators propel atoms to 99.9999% of light speed, confirming his predictions with terrifying precision. Objects genuinely gain mass. Time genuinely dilates. The regulations are absolute. Scientists have exhausted countless strategies seeking loopholes. They've developed exotic propulsion theories. They've calculated gravitational slingshot trajectories. They've proposed generation ships where entire civilizations would experience birth, life, and death during transit. None of these approaches modify the fundamental obstacle. Einstein's equations seal the door, and conventional physics cannot locate the key. Physicists characterize these laws as inviolable. Violate them, and you shatter causality itself. You generate paradoxes where consequences precede causes. You demolish the logical architecture maintaining reality's coherence. The universe would sooner collapse than permit massive objects to exceed light velocity. Time dilation exacerbates the situation. Even achieving 99% light speed means time flows differently for travelers than for people remaining home. A journey consuming 10 years for you might span decades or centuries on Earth. You would return discovering everyone you knew long deceased, their great-grandchildren now elderly. The isolation becomes complete. Length contraction introduces another reality-warping phenomenon. At extreme velocities, space itself appears compressed ahead of you. Distances shrink. A trip requiring years might subjectively feel like months to you, while decades elapse externally. The universe warps around rapidly moving objects in ways defying intuitive comprehension. For generations, physicists accepted this as physics' final verdict. Light speed constitutes the ultimate limit. Nothing escapes it. This principle became fundamental to every physics curriculum globally. Breaking it seemed as impossible as constructing square circles, or forcing 2 + 2 to equal 5. But certain scientists refused accepting permanent defeat. They began posing a different question. What if we're conceptualizing movement incorrectly? The energy nightmare. Accelerating even a modest spacecraft to light velocity demands more energy than currently exists in every fuel reservoir, battery and power station on Earth combined. Then multiply that total by 1 billion. You still fall catastrophically short. The mathematics underlying this nightmare scenario are confirmed and unshakable. As velocity increases, kinetic energy requirements don't merely grow, they explode. A spacecraft massing just 1 metric ton would require approximately 90 petajoules to reach light speed. That equals humanity's total annual energy production, consumed within seconds just to propel a small vehicle. Nuclear fusion, the identical process powering stars, offers our most energy-dense fuel source currently available. Yet even converting an entire large asteroid's mass into pure energy would barely accelerate a decent-sized starship to meaningful fractions of light speed. We're not discussing difficult engineering challenges, we're confronting fundamental physical impossibilities. Project Daedalus, designed during the 1970s, proposed fusion rockets reaching 12% of light velocity. This sounds modest until examining the design specifications. A vessel primarily consisting of fuel tanks matching skyscraper dimensions, carrying 50,000 metric tons of deuterium and helium-3. The payload compartment containing actual cargo and crew would be minuscule comparatively, and that massive ship would still require 2 decades reaching just our neighbouring star system's outer boundary. Antimatter engines could theoretically improve this fuel-to-payload ratio. When matter encounters antimatter, complete annihilation occurs, converting 100% of mass into energy. This represents the most efficient fuel theoretically achievable. The problem? We can only produce antimatter individual particles at a time using massive particle accelerators. Storing it requires magnetic containment systems consuming enormous power, continuously. Producing sufficient antimatter to fuel one interstellar mission would consume thousands of years using current technology. Certain physicists propose solar sails, enormous reflective surfaces pushed by stellar light pressure. These require zero fuel, just patience. The acceleration proves glacial, measured in fractions of millimeters per second, compounding across years. Reaching even 10% of light speed would demand decades of continuous acceleration. The sail would need to span miles across, impossibly thin, yet robust enough to resist tearing. Every conventional propulsion method encounters identical limitations. The faster you desire traveling, the more fuel you need. The more fuel you carry, the heavier your spacecraft becomes. The heavier your craft, the more energy you need for acceleration. Engineers call this diminishing returns. Philosophers might call it cosmic cruelty. Chemical rockets plateau around 5 kilometers per second. Ion drives might achieve 20 or 30. Nuclear thermal engines could potentially hit 50. Even the most optimistic fusion designs cap around 3,000 kilometers per second. Still merely 1% of light velocity. We're hurling pebbles at mountains hoping to move them. The energy trap isn't simply about constructing larger engines or discovering superior fuel. It represents a fundamental barrier encoded into reality's structure. Einstein's equations ensure that reaching light speed with any massive object demands infinite energy. Infinite means impossible. No clever engineering, no breakthrough technology, no amount of determination alters that equation. Yet the trap only exists if you play by conventional rules. What if movement itself isn't what we believe? Earth might be dying, and we possess no alternative destination. That cold fact keeps researchers awake nights because examining our cosmic neighborhood reveals a grim truth. Every other planet in our solar system constitutes a hostile wasteland. Mars, the nearest candidate, is a frozen desert with temperatures plunging to negative 125 degrees Celsius. Its atmosphere is 95% carbon dioxide, and so tenuous that standing on the surface equals being 35 kilometers high in Earth's atmosphere. Your blood would literally boil in the low pressure. Dust storms engulf the entire planet for months, and cosmic radiation bombards the surface constantly because Mars lost its protective magnetic shield billions of years ago. Venus presents even worse conditions. Beneath thick cloud layers, surface temperatures reach 465 degrees Celsius, hot enough to melt lead. Atmospheric pressure there equals being 1 kilometer underwater on Earth. The atmosphere itself is predominantly carbon dioxide mixed, with sulfuric acid clouds. Probes sent to Venus have survived less than 2 hours before being simultaneously crushed and melted. Living there isn't difficult, it's impossible. The gas giants offer no surface whatsoever to stand upon. Jupiter, Saturn, Uranus and Neptune are essentially enormous spheres of hydrogen and helium, with crushing pressures and winds exceeding 1,600 kilometers per hour. Their moons present marginally better options, but remain frozen, airless, and lethal. Titan, Saturn's largest moon, has liquid methane lakes and a thick atmosphere. This sounds promising until you realize surface temperatures sit at negative 179 degrees Celsius. You would freeze solid within seconds without protection. Europa, orbiting Jupiter, might harbor liquid water beneath miles of ice, but accessing it would require drilling through a frozen shell in one of the solar system's most radiation-saturated environments. Mercury oscillates between 430 degrees on its illuminated side and negative 180 degrees in shadow. Earth's moon has no atmosphere, no water, and faces identical radiation bombardment as Earth, but without any protective magnetic field. Every single body in our solar system is either too hot, too cold, too pressurized, or completely lacking basic requirements for human life. Terraforming these worlds remains pure speculation. Even optimistic estimates suggest making Mars barely habitable would consume thousands of years and require technology we haven't invented yet. We would need to thicken its atmosphere, warm its surface, restart its magnetic field, and create breathable air. Each step presents nearly insurmountable challenges. Earth isn't just our home, it's our only viable home for potentially millions of years into the future, even with unlimited technology. That means if climate change, asteroid impacts, or any other catastrophe makes Earth uninhabitable, humanity has no backup plan. We need to reach beyond our solar system, not just for exploration, but for survival. The problem, those potentially habitable worlds exist light years away. Proxima Centauri b orbits in its star's habitable zone, just 4.2 light-years distant. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 potentially habitable, 39 light-years away. Kepler 442b closely resembles Earth and sits 206 light-years distant. These worlds represent our future homes, but they might as well exist in another dimension with current technology. This is why faster-than-light travel isn't a luxury, it's an evolutionary necessity. We need new worlds, and reaching them demands breaking physics' most fundamental speed restriction. Paradise Beyond Reach telescopes have identified over 5,400 confirmed planets, orbiting distant stars, and dozens sit in habitable zones where liquid water could exist. We can observe them. We can measure their size, composition, and orbital characteristics. We can calculate their surface temperatures and atmospheric composition. We just cannot reach them. Proxima Centauri b haunts astronomers because it represents everything we desire and cannot have. Just 4.2 light-years away, this planet orbits a red dwarf star in the habitable zone. It might have oceans. It could harbour life. Early data suggests it might even possess a magnetic field protecting it from radiation. Scientists estimate it receives similar energy levels as Earth does from our Sun. The TRAPPIST-1 system, discovered in 2017, sparked even greater excitement. 7 Earth-sized planets orbit a small, cool star just 39 light-years away. 3 of those planets sit squarely in the habitable zone. Computer models suggest they could have atmospheres, weather systems, and stable climates. Liquid water isn't just possible but likely. Kepler 442b, nicknamed Earth's cousin, orbits a star remarkably similar to our own. It receives only 10% more energy than Earth gets, suggesting surface temperatures in the correct range for life. It sits 1,106 light-years distant, and discovering it felt like finding a twin sibling across an uncrossable ocean. These discoveries keep multiplying. Every year brings dozens of new candidates. Planets with thick atmospheres, worlds with day-night cycles similar to Earth, rocky planets with just the right mass to retain their air without crushing anything on the surface. We've found frozen worlds, lava worlds, ocean worlds, and desert worlds. The galaxy teems with possibilities, yet every single one remains completely unreachable. Even Proxima Centauri b, our closest candidate, requires 6,700 years to reach with current spacecraft speeds. TRAPPIST-1 would take 626,000 years. Kepler 442b demands 19 million years of continuous flight. These numbers stop being travel times and start becoming geological epochs. We're trapped behind glass watching paradise we cannot enter. Astronomers can describe the atmospheric composition of planets dozens of light-years away, but we cannot send even a small probe to investigate them in anything resembling a reasonable time frame. The James Webb Space Telescope can photograph chemical signatures of water vapor and oxygen in alien atmospheres, yet physically visiting those worlds remains pure fantasy. The frustration transcends scientific curiosity. These planets represent potential homes for future generations. They could be refuges if Earth becomes uninhabitable. They might harbour ecosystems we could study, resources we could use, or even intelligent civilizations we could contact. Everything we want to know, everything we need to reach, sits just beyond our grasp behind an insurmountable wall of distance and physics. Radio. Signals travelling at light speed would take years to reach these worlds. Even if we detected intelligent life today and transmitted a message, their reply wouldn't arrive until decades later. A conversation would span generations. Physical travel seems impossible without completely reimagining how movement works. Unless we stop trying to move through space and start moving space itself. The Alcubierre Revolution. Miguel Alcubierre was a graduate student obsessed with Star Trek when he decided to actually calculate whether warp drive could function in real physics. In 1994, he published a paper that made professional physicists pause and reconsider, because his mathematics wasn't just creative, it was technically valid. The Alcubierre's drive concept doesn't accelerate a spacecraft through space whatsoever. Instead, it creates a bubble around the ship that warps space itself. Space contracts ahead of the vessel and expands behind it, creating a wave that carries the bubble forward. The ship inside remains stationary relative to the space immediately surrounding it, experiencing zero acceleration forces whatsoever. Consider a surfer riding a wave. The surfer isn't swimming through water or generating their own speed. They're being carried by the wave itself, standing motionless on their board while the ocean does all the work. Alcubierre's equations described a spacecraft riding a wave through space-time in exactly the same manner. The brilliance comes from exploiting a loophole in Einstein's equations. Relativity states nothing with mass can move through space faster than light. Acceptable. But Einstein never claimed space itself cannot move faster than light. In fact, cosmologists know space expands faster than light at the observable universe's edges. That expansion is how the universe grew from a tiny point to its current size in just under 14 billion years. If space can already break the speed limit, why not harness that property? Alcubierre's equations demonstrated you could theoretically create negative energy density ahead of a ship, causing space to contract there, while positive energy behind causes expansion. The bubble containing the ship gets propelled forward by this asymmetric space-time distortion. No thrust needed, no acceleration felt. The ship simply rides the wave. His paper sent shock waves through theoretical physics. For the first time, someone had described a faster-than-light travel mechanism using accepted general relativity equations. It wasn't speculative science fiction. It was peer-reviewed mathematics published in a legitimate physics journal. The method appeared technically legal according to known physics laws. Other scientists rushed to verify his calculations. They found the math held up. Spacetime could theoretically be warped in this way without violating causality or breaking relativity. The energy requirements absolutely astronomical but technically finite. That represented a massive improvement over conventional propulsion, which requires literally infinite energy to reach light speed. The Alcubierre drive could theoretically reach any speed. 10 times light speed, 100 times, 1,000 times. The bubble isn't moving through space, so relativistic effects like time dilation and length contraction don't apply. Crew members inside would experience normal time flow. They wouldn't age, slower than people back home. They wouldn't see distances compress. Physics inside the bubble remains completely normal. Alcubierre himself admitted he never expected the concept to work mathematically. He was just a physics student playing with equations inspired by his favourite television show. Yet his recreational calculation accidentally revealed a genuine possibility hidden in space-time structure itself. Reality appeared to have a cheat code embedded in its operating system. Of course, actually building one presented complications that made the theory look almost easy by comparison. But the door was open. The impossible suddenly looked merely extremely difficult, warping reality. Space-time isn't empty nothingness. It's an actual thing, a fabric that can bend, stretch, twist, and ripple. Every massive object creates a depression in this fabric like bowling balls resting on a stretched sheet. That depression is what we experience as gravity. Einstein described this over a century ago, and we've confirmed it countless times. GPS satellites must account for time flowing slightly faster in orbit than on Earth's surface, because they sit higher in the gravitational well. Experiments with atomic clocks on airplanes show the same effect. Black holes warp spacetime so severely that nothing can escape once you cross the event horizon. The Alcubierre drive takes this concept and weaponizes it. Instead of letting gravity naturally warp space, you artificially create a bubble of warped space around your spacecraft. The warp contracts space ahead of you and expands it behind you, generating a wave that pushes the bubble forward. Your ship never moves. Through space. Space moves around the ship. This sounds like semantics until you realize this sidesteps Einstein's speed limit completely. Relativity restricts movement through space, but places no limits on how fast space itself can move. The distinction matters because all those nightmare side effects of near-light speed travel, time dilation, length contraction, infinite energy requirements, all disappear when you're not actually moving. Inside the warp bubble, physics operates normally. You can walk around the ship, drink coffee, play cards, and experience time flowing at exactly the same rate as people back on Earth. No twin paradox where you return younger than your siblings. No relativistic effect smearing your vision. The bubble isolates you from the extreme space-time distortions happening at its edges, The wave itself could move at any speed. Alcubierre's original calculations suggested 10 times the speed of light would be relatively achievable. More recent variations have proposed speeds reaching 100 or even 1,000 times faster. At those velocities, Proxima Centauri becomes a 2-week trip. The entire Milky Way galaxy becomes crossable in a human lifetime. The warp bubble would appear strange to outside observers. Light cannot normally escape from the region of highly compressed space ahead of the ship, making it partially invisible. The expanding space behind would redshift light to radio wavelengths. The bubble might emit exotic radiation as it moved, creating a visible wake through spacetime itself. From inside, you would see space compressed ahead of you, making distant destinations appear closer than they actually are. Stars would shift color as their light gets distorted by the warp field. Looking backwards, space would appear to stretch away into infinity, though you would still see your starting point just at shifted wavelengths. The mathematics describing this get complex quickly, involving tensor equations and differential geometry. But the core concept remains beautifully simple. Surf space-time like an ocean wave, letting the universe do the work while you sit comfortably inside a bubble of normal reality. The key lies in creating asymmetric space-time curvature. That requires manipulating the energy density of space itself in ways that seem almost magical. Which brings us to the biggest problem with the entire concept. The exotic matter problem. Alcubierre's warp drive requires something that probably doesn't exist. Exotic matter with negative mass and negative energy density. This isn't antimatter, which annihilates regular matter in bursts of energy. This is something far stranger that repels instead of attracts, pushes instead of pulls, and makes gravity work backward. Normal matter curves space-time inward, creating the gravitational wells that hold planets in orbit, and make apples fall from trees. Exotic matter would curve space-time outward, creating a gravitational hill that pushes things away. It represents the opposite of everything we know about how mass and energy behave in our universe. Does negative mass exist? We've never observed it directly. No one has ever measured it, created it, or found evidence of it occurring naturally anywhere in the cosmos. It remains entirely theoretical, a mathematical possibility that general relativity equations permit, but nature has apparently never bothered to manifest. The amount needed for a warp drive makes things worse. Alcubierre's original calculations suggested you would need negative mass equivalent to the total mass energy of Jupiter just to warp space around a small spacecraft. Jupiter weighs 318 times more than Earth. Converting that much normal matter into exotic matter, even if possible, would require energy expenditures dwarfing anything humanity could generate. Critics pounced on this requirement immediately. Sure, the math works, they said. The equations are valid, but demanding materials that don't exist makes the whole concept useless. You might as well design a perpetual motion machine that runs on unicorn tears. The physics checks out, but the ingredients are fantasy. Some researchers tried to find alternatives. Could you use intense electromagnetic fields to create negative energy density in vacuum? Maybe quantum fluctuations could be manipulated to generate the required effect. Dark energy, the mysterious force accelerating the universe's expansion, exhibits some properties similar to negative pressure. Could we somehow harness or concentrate it? These questions generated decades of theoretical papers, but no practical answers. Creating sustained regions of negative energy density appeared to violate several fundamental principles, including quantum field theory's energy conditions. The universe seems to have built-in protections preventing large-scale negative energy concentrations, probably to avoid causality violations and other reality-breaking paradoxes. The Casimir effect offered a tiny glimmer of hope. When you place two uncharged metal plates extremely close together in vacuum, quantum fluctuations between them create less energy density than in the surrounding space. That technically counts as negative relative energy density, though the absolute value remains positive. The effect is measurable, confirmed, and absolutely real. Could this principle be scaled up? If you could create and manipulate Casimir-like effects on large scales, you might generate the space-time distortions needed for a warp bubble without requiring exotic matter at all. The energy would still need to come from somewhere, but at least you would be working with known physics rather than theoretical ghosts. This is where Harold White enters the story, and where everything changes from pure theory to something approaching experimental physics. The NASA breakthrough Dr. Harold White spent years researching propulsion physics at NASA's Johnson Space Center in Houston. His team operated a lab dedicated to investigating exotic propulsion concepts, the kind of fringe science that makes colleagues raise eyebrows but occasionally produces breakthrough discoveries. In 2011, White published new calculations suggesting the energy requirements for an Alcubierre drive might be dramatically lower than originally thought. His revised math showed that optimizing the shape of the warp bubble could reduce energy needs by several orders of magnitude. Instead of requiring Jupiter mass amounts of exotic matter, you might only need several hundred kilograms. Still exotic, still unavailable, but suddenly the concept shifted from physically impossible to merely incredibly difficult. Then in 2021, something unexpected happened. White's team was studying the Casimir effect using specialized equipment designed to measure nanoscale forces between metal plates. They weren't trying to create a warp bubble. They were investigating whether Casimir forces could be useful for spacecraft attitude control. Basic research, nothing revolutionary. During one experimental run, their sensors detected something bizarre, a measurable warp in spacetime at the nanometer scale. The readings matched theoretical predictions for what a tiny warp bubble would look like. They had accidentally created the exact space-time geometry that Alcubierre described, just at a scale millions of times smaller than needed for actual propulsion. White's team repeated the experiment multiple times. The effect remained consistent and measurable. They weren't seeing instrument errors or quantum noise. They were observing actual repeatable space-time distortion created by manipulating the Casimir effect. A warp bubble, microscopic but real, had appeared in a laboratory on Earth. The implications detonated through the propulsion physics community. Warp drive. Geometry wasn't just theoretical anymore. It could be created, measured, and studied experimentally. If you could make a nanoscale warp bubble, then scaling it up became an engineering challenge rather than a physics impossibility. Critics demanded verification. Other labs needed to reproduce the results before anyone could claim definitive proof. The equipment required is specialized and expensive, so independent confirmation takes time. Some physicists suggested alternative explanations for White's readings. Maybe electromagnetic interference, maybe quantum effects being misinterpreted. Skepticism remains healthy in science. Yet White's team had calibrated their instruments carefully, accounted for known sources of error, and documented everything meticulously. The data looked solid. More importantly, the effect appeared when theory predicted it should, and vanished when conditions changed. That kind of correlation suggests real phenomena rather than measurement artifacts. NASA quietly increased funding for White's lab. Other government agencies took notice. Private aerospace companies started hiring propulsion physicists to investigate warp field generation. The race was on, not to build a warp drive immediately, but to understand whether scaling up from nano to macro was achievable. The exotic matter problem still loomed large. Even at reduced energy requirements, you still needed negative energy density to create asymmetric spacetime curvature. White's experiments showed Casimir effects could produce warp-like geometry, but only at tiny scales with tiny amounts of energy manipulation. Going from nanometers to meters represented a billion-fold increase in scale. Still, the psychological barrier had shattered. Warp bubbles existed in reality, not just on paper. That changed everything. Suddenly, other research teams started dusting off old warp drive papers and looking for overlooked details. Maybe the answer was hiding in plain sight all along. Quantum vacuum energy. The Casimir effect sounds like magic, but emerges from one of the weirdest confirmed facts about reality. Empty space isn't empty. Quantum field theory says vacuum constantly churns with virtual particles popping into and out of existence. These particles exist for infinitesimally brief moments, borrowing energy from quantum uncertainty, then disappearing before the universe notices the debt. You cannot see these virtual particles directly, but you can detect their effects. They create a faint background energy that permeates all of space. Normally, this quantum vacuum energy is uniform, pushing equally in all directions, so you never notice it. But in 1948, Dutch physicist Hendrik Casimir predicted something strange would happen if you placed two uncharged metal plates very close together. The metal plates would restrict which virtual particles could exist in the gap between them. Only particles with wavelengths smaller than the gap could appear there. Outside the plates, all wavelengths of virtual particles could exist freely. This creates an imbalance, more quantum pressure pushing the plates together from outside than pushing them apart from inside. The result? The plates attract each other with measurable force, despite having no electric charge and no conventional interaction. They're being pushed together by an imbalance in quantum vacuum fluctuations. This force is tiny, only noticeable when plates are separated by distances smaller than a human hair, but it's absolutely real and has been measured countless times. The Casimir effect proves negative energy density can exist in nature. The space between those plates has less quantum vacuum energy than normal empty space. That technically counts as negative energy relative to the surrounding vacuum. This is crucial because it suggests exotic matter might not be required for warp drives if you could amplify and control Casimir-like effects. White's experiments exploited this principle by carefully arranging capacitor plates in specific geometries. His team created regions where quantum vacuum energy differed from baseline. Those differences in energy density warped space-time slightly, creating measurable distortions. The warp was microscopic, but it was there. Scaling this up presents enormous challenges. The Casimir force drops off rapidly with distance. Move the plates even slightly farther apart and the effect vanishes. Creating Casimir-like negative energy densities across distances measured in meters rather than nanometers would require completely new techniques, possibly involving exotic materials or quantum technologies that don't exist yet. Some physicists proposed using metamaterials, artificially structured materials that bend light and electromagnetic fields in unusual ways. Others suggested quantum computing techniques might allow precise control over vacuum fluctuations. A few radical thinkers wondered if dark energy, the mysterious force accelerating the universe's expansion, could be related to manipulable vacuum energy states. The energy requirements remain staggering, even with Casimir effects reducing them. You still need to create and maintain sharp energy gradients across the warp bubble boundary. That demands power sources far beyond anything currently available. Nuclear fusion might provide enough concentrated energy, but controlling it precisely enough to shape spacetime represents an entirely different challenge. Yet the door was open. Exotic matter might not be necessary after all. Real, measurable physics could potentially create warp-like spacetime distortions. The path from nanoscale demonstration to spacecraft-scale application looked long and uncertain, but it existed. That represented genuine progress, not just theoretical speculation. The next breakthrough would come from an unexpected direction, listening to the universe itself for signs that someone else might have already solved the problem, optimizing the impossible. When Alcubierre first calculated the energy requirements for his warp drive, the numbers were apocalyptic. You would need to convert the entire mass of Jupiter into pure energy and somehow concentrate it into exotic matter. That equals about 1.9 × 1047 joules of energy. For perspective, the most powerful nuclear weapon ever detonated released about 2.1 × 1017 joules. You would need that bomb's energy output multiplied by 1 trillion times. Those numbers killed serious interest immediately. Sure, the math was elegant and the concept legal according to relativity, but requiring more energy than multiple star cores made the whole concept a theoretical curiosity. Building it seemed as realistic as constructing a ladder to the moon. But Harold White noticed something in the equations. The energy requirements depended heavily on two factors: the thickness of the warp bubble wall and the overall shape of the bubble geometry. Alcubierre's original model used relatively thick walls and a simple spherical shape because that made the math cleaner. What if you optimized those parameters? White proposed reshaping the bubble into a toroidal configuration, like a donut rather than a sphere. He calculated that making the bubble wall oscillate in thickness rather than remaining static could dramatically reduce energy needs. The math got significantly more complex, but computers could handle it. When he ran the optimized numbers, the results shocked everyone. Energy requirements dropped from Jupiter mass to something closer to 500 kilograms of exotic matter equivalent. Still enormous, still exotic, but several orders of magnitude more reasonable than before. That mass equals about a small satellite. You could theoretically fit it inside a spacecraft rather than needing a planet-sized energy source. Further refinements continued improving the outlook. Different research groups proposed various bubble geometries, elongated ellipsoids, figure-8 configurations, nested shells with different densities. Each optimization chipped away at the energy requirements. Some recent papers suggest you might only need several dozen kilograms of negative energy density if you get the geometry precisely right. These improvements happened purely through mathematical optimization, finding more efficient ways to warp spacetime that achieve the same propulsive effect with less energy input. It mirrors how engineers improved rocket efficiency over decades by refining nozzle shapes, fuel mixture ratios, and combustion chamber designs. The fundamental physics remained the same, but clever optimization extracted better performance. The really exciting development came when researchers realized you might not need sustained exotic matter at all. Some models suggest you could use ordinary energy to create temporary regions of negative energy density through quantum effects, maintaining them just long enough to generate thrust, then letting them collapse and recreating them. Think of it like internal combustion engines that burn fuel in pulses rather than continuous combustion. This pulsed warp drive concept could theoretically run on advanced fusion reactors or antimatter annihilation without requiring exotic matter storage. You would need exotic effects, but only transiently and in controlled ways. That shifts the challenge from material science to precision engineering. Could these optimizations really work? The mathematics appears sound, confirmed by multiple independent physicists. But math only tells you what might be possible according to known laws. Whether reality cooperates with these theoretical models remains unproven until someone builds working hardware. Still, dropping energy requirements from Jupiter mass to satellite mass represents genuine progress. It moved warp drives from impossible to merely extraordinarily difficult. Sometimes that distinction makes all the difference. Alternative approaches. Other research teams were approaching the problem from entirely different angles. Brazilian physicist José Natario looked at Alcubierre's equations and saw room for improvement. In 2002, he published an alternative warp drive model using different geometric techniques to achieve similar results. The Natario drive, as it became known, creates space-time distortions through a modified tensor field configuration that some physicists argue is more stable than Alcubierre's original design. The key difference lies in how the warp bubble interfaces with normal space-time. Alcubierre's model creates sharp discontinuities at the bubble boundary, where space abruptly transitions from compressed to normal to expanded states. Those sharp boundaries require intense energy, concentrations, and might generate problematic radiation or gravitational effects. Natario smoothed out those transitions. His model distributes the space-time distortion more gradually across a larger volume, reducing the peak energy densities required at any single point. Think of it like the difference between a sharp cliff edge and a gentle slope. Both change elevation, but the slope is more stable and requires less dramatic engineering to traverse. This geometric revision carries important implications for theoretical stability. Sharp energy boundaries in Alcubierre's model might be prone to quantum instabilities or spontaneous decay. Smoother distributions might maintain themselves more readily. The Natario drive also apparently reduces some secondary effects like Hawking radiation that could occur at the warp bubble boundaries. Energy requirements in the Natario model remain comparable to optimized Alcubierre drives, but the engineering challenges differ. You need to create gentler but more spatially extended warping of spacetime. This might actually be easier to achieve using Casimir-like effects or electromagnetic field manipulation because you're not demanding extreme energy concentrations at specific points. Some researchers suggest the ideal solution might combine elements from both models. Use Natario's smooth boundary geometry to improve stability, while incorporating Alcubierre's oscillating bubble walls to minimize energy requirements. Hybrid designs could potentially offer benefits from both approaches. The diversity of proposed models suggests warp drive physics is maturing from a single wild idea into a genuine field of study with multiple competing approaches. That diversity is healthy. Different geometries might prove optimal for different purposes. Short-range warp jumps might use one configuration, while long-distance interstellar voyages use another. Listening for alien warp drives. The next question researchers started asking was whether anyone else in the universe might have already figured this out, and if so, could we detect the evidence they left behind? Gravitational waves ripple through space-time when massive objects accelerate violently. Colliding black holes, merging neutron stars and supernovae all broadcast these ripples across the cosmos at light speed. We can now detect them using observatories like LIGO and Virgo, which measure space-time distortions smaller than a proton's diameter. In 2024, a research team at Germany's University of Potsdam had a clever idea. If warp drives warp space-time, they should also generate gravitational waves. The pattern would be distinctive, different from natural astronomical sources. A moving warp bubble would create a specific signature in the gravitational wave spectrum based on its geometry and speed. The researchers ran simulations showing exactly what these warp drive signatures would look like in gravitational wave detectors. They calculated the frequencies, amplitudes, and polarization patterns that different warp drive designs would produce. Then they started examining existing gravitational wave data, searching for matches. Nothing turned up in current archives, but gravitational wave astronomy is still young. LIGO only achieved its first detection in 2015. We've barely begun listening to the universe in this new way. Advanced detectors coming online in the next decade will be far more sensitive, capable of hearing fainter signals and distinguishing more complex patterns. If any advanced civilization within a few billion light years has developed warp drive technology, we might detect their ships moving through space by the gravitational ripples they leave behind. Those ripples would propagate outward at light speed, creating expanding shells of distorted space-time that eventually wash over Earth. The implications are staggering. We could discover faster-than-light travel is real, not by inventing it ourselves, but by detecting alien civilizations already using it. Each detection would provide clues about how they built their warp drives, the energy signatures, the bubble geometries, the propulsion methods. It would be like finding alien footprints and reverse engineering their shoes. Some critics argue that civilizations advanced enough to build warp drives would probably be careful about detection. Maybe they shield their gravitational signatures or use modified warp geometries that minimize detectable emissions. Perhaps they avoid traveling through populated regions of the galaxy at warp speed to prevent accidentally revealing themselves. But even careful civilizations might leave occasional traces. A single unshielded warp jump, an emergency maneuver, or simply an old primitive warp drive from their early development could produce detectable signals. We only need to observe one clear example to prove the concept works in physical reality. The search expands beyond just gravitational waves. Warp bubbles moving at extreme speeds through interstellar gas and dust should create shock waves and radiation signatures. High-energy particles accelerating at the bubble boundary might produce gamma rays or cosmic ray bursts. Optical telescopes could search for the characteristic red and blue shifting of light around moving warp fields. No confirmed detections yet. The universe appears quiet on these frequencies, at least in the data we've examined so far. But absence of evidence isn't evidence of absence, especially when we've only been listening seriously for a few years using limited sensitivity equipment. The paradox problem. Faster-than-light travel terrifies some physicists because it might allow time travel, and time travel creates logical impossibilities that threaten reality's consistency itself. The grandfather paradox illustrates this perfectly. If you travel back in time and prevent your grandfather from meeting your grandmother, you never get born. But if you were never born, you never travelled back in time. But then your grandfather does meet your grandmother, so you do get born, creating an infinite loop with no consistent resolution. Warp drives potentially enable similar paradoxes on cosmic scales. If you travel faster than light between two reference frames moving relative to each other, you could theoretically arrive before you left according to certain observers. The math gets complex fast, involving closed time-like curves and violations of causality. Some physicists argue this connection proves faster-than-light travel must be impossible. The universe cannot permit causality violations because they create logical contradictions. If effects can precede causes, then nothing makes sense. You could receive answers before asking questions, die before being born, or prevent events that already happened. Reality would collapse into incoherence. Stephen Hawking proposed a chronology protection conjecture, suggesting unknown physics prevents time travel, even if equations appear to allow it. Whenever someone tries to create a time machine or travel faster than light, quantum effects or other mechanisms would intervene to prevent paradoxes. The universe protects its own consistency. Other scientists point out that warp drives might naturally avoid paradoxes through their specific geometry. The space inside the bubble moves faster than light relative to outside space, but nothing crosses the light speed barrier locally. Information cannot propagate backward in time through the bubble, because the bubble isolates its interior from external reference frames. Additionally, warp drives require continuous energy input to maintain the space-time distortion. That energy must come from somewhere, usually fusion or antimatter reactions happening in real time. You cannot retroactively provide energy to a warp bubble that already collapsed. This temporal directionality might inherently prevent backward time travel, even if you move faster than light. The honest answer is, we don't know whether faster-than-light travel creates paradoxes because we've never achieved it. The universe might have protection mechanisms we haven't imagined. What remains certain is that building a working warp drive would immediately illuminate these questions. Either paradoxes emerge and we learn new physics explaining them, or they don't emerge and we learn causality protection is built into space-time. Life inside the bubble. The interior of a warp bubble would feel absolutely ordinary. You couldn't tell whether the bubble was moving at 10 times light speed or sitting completely still. Physics inside operates exactly like physics on Earth, because the space-time inside remains flat and undistorted. The extreme warping happens only at the boundary, creating a protective shell around normal reality. Your watch would tick at the same rate as watches back on Earth. Your cells would age normally. Chemical reactions would proceed at standard speeds. Light would travel at its usual velocity relative to the bubble interior. Nothing about the fundamental constants of physics would change. You exist in a pocket of normal space-time that happens to be moving through the larger universe. This isolation from external reference frames creates interesting communication challenges. Radio signals from inside the bubble, trying to reach outside, would need to cross the boundary where space-time curves dramatically. That transition might block electromagnetic radiation entirely, making the bubble opaque to conventional communications. You would essentially be cut off during transit, unable to send or receive messages until dropping out of warp. Looking out windows would present bizarre visuals. Light from stars ahead would be massively blue-shifted, compressed into gamma rays by the space-time contraction in front of the bubble. Stars behind would redshift into radio waves, stretched by spatial expansion. The visible spectrum would narrow to a ring around your direction of travel, possibly showing distorted, smeared views of the cosmos. Some models suggest you might see nothing at all through forward-facing windows. The compressed space ahead could create an event horizon-like effect, where light cannot escape the warp field to reach your eyes. You might fly blind, navigating by instruments rather than direct observation. The gravity inside would match whatever artificial gravity systems you installed, or be zero if you have none. The warp field itself doesn't create internal gravitational effects because space-time inside remains flat. This differs dramatically from natural gravitational fields, where space-time curvature causes observable effects throughout the region. Crew psychology might be the biggest challenge. Being isolated in a bubble of normal physics, while the universe restructures around you, could feel profoundly unnerving. Some astronauts might experience existential anxiety from knowing they exist in a tiny pocket of reality, insulated from the larger cosmos. Training would emphasize maintaining routines and psychological stability during what amounts to sensory deprivation from the external universe. Who's building it now? NASA's Advanced Propulsion Physics Laboratory operated quietly for years under Harold White's direction, tucked away in Building 9 at Johnson Space Center in Houston. The official mission sounded mundane: study exotic propulsion concepts for potential future applications. The unofficial reality involved active warp drive research funded through carefully worded budget requests. Then came the 2021 announcement about detecting warp bubble signatures in the lab. Suddenly the work wasn't so quiet anymore. Media coverage forced NASA to either disavow the research or acknowledge its legitimacy. They chose a middle path, confirming the research exists while emphasizing its extremely preliminary nature and decades-long timeline to potential applications. Behind closed doors, funding reportedly increased. More physicists joined the team. Equipment orders expanded. Other NASA centers got involved. Glenn Research Center in Ohio brings propulsion expertise, jet propulsion. Laboratory in California brings advanced engineering capabilities. Ames Research Center contributes computational modeling resources. Government classification adds murky layers. Some warp drive research likely proceeds behind security clearances, invisible to public oversight. If breakthrough discoveries occur in classified programs, we might not learn about them for years or decades. Military applications of faster-than-light travel are obvious enough that defense agencies certainly fund their own parallel research. But government labs aren't the only ones chasing this dream anymore. Elon Musk rarely discusses warp drives publicly, but SpaceX's long-term plans for Mars colonization and beyond suggest someone there is thinking about faster propulsion. The company employs some of the world's best propulsion engineers and theoretical physicists. If any private organization would seriously pursue warp drive research, SpaceX tops the list. Blue Origin, Jeff Bezos' space company, presumably conducts similar research. Other aerospace companies like Lockheed Martin, Boeing, and Northrop Grumman maintain advanced concepts divisions that explore exotic propulsion. Private research avoids some government bureaucracy and classification restrictions, enabling faster iteration and more risk-taking. The race is on, though conducted mostly in secrecy. Whoever achieves the first breakthrough will either become incomprehensibly wealthy and powerful, or spark a new era of space exploration that transforms humanity. Possibly both. The path forward. So where do we actually stand? Every breakthrough brings new timelines and predictions. Optimists claim working warp drive prototypes could appear within 10 to 15 years if research continues at current pace. Pessimists argue we're centuries away from practical applications. The truth likely falls somewhere between. Energy generation represents the most immediate challenge. Even with optimized geometries and reduced requirements, warp drives need enormous power output controlled with extreme precision. Current fusion research progresses steadily, but hasn't achieved sustained net energy gain yet. Antimatter production remains painfully slow and expensive. Dark energy manipulation exists only in theoretical papers. Creating negative energy density at useful scales presents an even harder problem. White's team detected nanoscale warp geometry, but scaling up by a factor of 10 billion seems impossibly difficult. The Casimir effect weakens rapidly with distance. Amplification techniques remain purely speculative. Material science faces extreme demands too. Any spacecraft surrounded by intense warp fields would experience stresses and radiation unlike anything current materials can withstand. Designing materials that survive these conditions will require extensive testing that cannot begin until we can generate warp fields to test them against. Navigation and control systems need complete reinvention. How do you steer when you cannot see your destination? How do you avoid collisions while traveling faster than light? What happens if something goes wrong inside a warp bubble moving at 10 times light speed? Theoretical physics still has gaps that make predictions uncertain. We cannot fully simulate warp drive dynamics using current equations. Quantum effects at bubble boundaries remain poorly understood. Whether dark energy actually helps or creates new problems is unknown. International cooperation would accelerate progress but remains unlikely given national security concerns. Funding levels matter enormously. Current warp drive research operates on budgets measuring millions annually across all programs worldwide. If humanity committed Apollo-level resources to warp drives, 10-year timelines might be achievable. Some researchers privately admit that a single critical breakthrough could change everything overnight. If someone discovers how to generate scalable, negative energy density, or learns to manipulate dark energy, or finds some completely unexpected space-time manipulation technique, the entire timeline collapses. We could go from barely able to measure nanoscale effects to building test vehicles within a few years. History shows technological revolutions often happen faster than experts predict, once key enabling discoveries occur. Powered flight went from barely possible to routine in 2 decades. Nuclear energy became practical within 5 years of theoretical understanding. The right breakthrough triggers explosive progress. What it means for humanity. Faster-than-light travel represents more than just technical achievement. It fundamentally transforms what humanity can become. Every great migration in our history, from Africa to every continent, across oceans to new worlds, expanded our potential and forced us to adapt and innovate. The stars represent our next frontier, but only if we can reach them. With warp drives, the galaxy opens up. Hundreds of potentially habitable planets within 50 light-years become accessible destinations. We could establish colonies on worlds better suited to life than Mars ever will be. Humanity would spread across multiple star systems, ensuring our survival even if disaster strikes Earth. The economic implications stagger the imagination. Asteroid mining becomes trivial when you can warp to the asteroid belt and back in hours. Rare elements abundant in other solar systems could be harvested and returned. Energy resources available from stars or gas giants far exceed anything Earth provides. scientific discovery would accelerate dramatically. Direct study of alien ecosystems, close observation of stellar phenomena, hands-on investigation of black holes and neutron stars all become possible. Questions about life's origins, planetary formation, and cosmic evolution could be answered through direct observation rather than distant speculation. Contact with alien civilizations becomes likely if they exist within our reach. Instead of waiting centuries for radio signals to cross space, we could physically visit nearby systems and search for life directly. We might find ruins of extinct civilizations, encounter primitive life, or make contact with intelligence equal or superior to ours. The risks cannot be ignored. Warp drive might enable terrifying weapon systems. Nations or groups with this technology would dominate those without. We need frameworks for preventing militarization before the technology matures, though history suggests such efforts usually fail. Environmental consequences remain unknown. Does repeated warp travel damage space-time? Could we accidentally destabilize regions of space through overuse? We need to study these questions before deploying the technology widely. The moment of truth. This moment in history, right now as the researchers inch toward functional warp drive physics, might be looked back upon as the pivot point where humanity's future trajectory shifted permanently. Either we solve this challenge and become a stellar civilization, or we remain confined to our solar neighborhood, perhaps forever. The choice isn't really ours. We can fund research and push boundaries, but the universe decides whether the physics allows what we need. Reality might simply not permit warp drives no matter how cleverly we try, or it might have already provided everything necessary, waiting for us to figure out the combination that unlocks it. Think about where we stand. A century ago, Einstein wrote equations that seemed to imprison us forever at subliminal speeds. 50 years ago, those equations were accepted as absolute law. 30 years ago, Alcubierre showed a mathematical loophole. 10 years ago, NASA started seriously investigating the possibility. 2 years ago, they detected actual warp bubble geometry in a laboratory. The progression is undeniable. We're not just dreaming anymore. We're experimenting, measuring, refining. The gap between theory and reality shrinks with each passing year. The question isn't whether warp drives are theoretically possible. We know they are, at least mathematically. The question is whether we can engineer them into physical existence. Someone reading this might be the person who solves it. Maybe you're the engineer who designs the first scalable negative energy generator. Maybe you're the physicist who cracks dark energy manipulation. Maybe you're the programmer who writes the code enabling real-time warp field control. The breakthrough could come from anywhere, from anyone with curiosity and determination. The universe is incomprehensibly vast. Light from the edge of the observable cosmos has been travelling toward us for over 13 billion years and will never arrive because space expands faster than light can cross it. We exist in a tiny bubble of causally connected space, able to interact only with the limited region where light has had time to reach since the Big Bang. Warp drives wouldn't change those cosmic limits. Even at 1,000 times light speed, the observable universe would take millions of years to cross. But they would transform what's practically achievable for human civilization, operating on human timescales. The nearby galaxy, containing billions of worlds, would finally be accessible. That's the prize we're chasing. Not infinite reach or godlike power, but simply the ability to explore our cosmic neighborhood within lifetimes, rather than millennia. We want to visit a few dozen nearby stars, investigate planets that telescopes show look promising, and establish humanity among the stars while Earth remains our home. Every technological revolution seemed impossible before it happened. Heavier-than-air flight violated common sense until it didn't. Splitting the atom was purely theoretical, until it wasn't. Landing humans on the moon was science fiction, until footprints appeared in lunar dust. Each time, the impossible became merely difficult, then difficult became routine. We stand at that same threshold now with warp drives. The mathematics work. The theory holds. Small-scale effects have been detected. The path from here to there remains unclear, filled with challenges that might take decades to overcome. But the path exists. That's what matters. The laboratory results from NASA's team weren't just academic curiosities. They were proof-of-concept demonstrations showing that the fabric of space-time can be manipulated in precisely the ways warp drive theory requires. The scale is wrong, nanometers instead of meters. The duration is wrong, microseconds instead of hours. The energy is wrong, milliwatts instead of gigawatts. But the fundamental phenomenon is there, real and measurable. Scaling up represents an engineering challenge, and humanity has proven remarkably good at engineering challenges once we understand the basic physics. We went from the Wright brothers' first flight to landing on the moon in 66 years. We went from the first nuclear reactor to nuclear power plants in 12 years. We went from room-sized computers to smartphones in 40 years. The timeline for warp drives might be longer. The challenges are certainly more fundamental, but the pattern holds. Once you prove something is possible at small scales, reaching large scales becomes a matter of resources, creativity, and persistence. The final calculation. Here's what we know for certain. Space-time can be warped. Negative energy density exists in nature through the Casimir effect. The mathematics of general relativity permit faster-than-light travel through space-time manipulation without violating causality. Laboratory equipment has detected warp bubble geometry at nanoscales. Energy requirements have dropped by orders of magnitude through geometric optimization. Here's what we don't know. Whether Casimir effects can scale to useful sizes, whether dark energy can be harnessed, whether materials can withstand the stresses at warp bubble boundaries, whether quantum effects will create unforeseen obstacles, whether the universe has hidden protection mechanisms preventing large-scale space-time manipulation. The ratio of knowns to unknowns has been shifting steadily in favor of knowns. 20 years ago, warp drives were pure speculation with no experimental basis whatsoever. 10 years ago, they were interesting. Mathematics with no path to reality. 5 years ago, they were theoretical possibilities with some optimization work. Today, they're experimental phenomena being studied in laboratories with government funding. The trajectory is clear. The unknowns are shrinking. Each year brings new papers, new experiments, new refinements to the theory. Each year eliminates potential obstacles and identifies new approaches. The field is accelerating, not stagnating. Private companies entering the space creates additional momentum. When profit-driven organizations start hiring warp drive physicists, they're betting real money on eventual success. They're not philanthropic organizations funding pure science for humanity's benefit. They're businesses expecting returns on investment. That suggests insider confidence exceeds what public statements admit. The international dimension adds urgency. Multiple nations pursuing this technology creates a race dynamic that accelerates progress. No country wants to be left behind when competitors achieve breakthrough capabilities. That competitive pressure, while potentially dangerous, also ensures resources keep flowing into research even when progress seems slow. The choice ahead. We stand at a crossroads. One path leads to continued confinement within our solar system, Yongji trapped by the tyranny of distance and the speed of light. We become a civilization that can see paradise but never touch it, that knows thousands of potentially habitable worlds exist but can never reach them, that remains forever vulnerable to any catastrophe that makes Earth uninhabitable. The other path leads to the stars, not in some distant future measured in millennia, but potentially within this century, not as a far-fetched dream, but as an engineering challenge with known physics and experimental validation, not as science fiction, but as the next great human achievement waiting to be unlocked. The choice between these paths isn't made through grand declarations or political decisions. It's made through funding allocations, through graduate students choosing research topics, through engineers taking jobs at aerospace companies, through public support for space, science, through maintaining curiosity about what's possible. Every dollar allocated to warp drive research is a vote for the second path. Every student entering physics or aerospace engineering is a vote for the second path. Every successful experiment, every published paper, every incremental improvement in our understanding pushes us further down that path toward the stars. The frustrating truth is that we won't know which path we're actually on until we either succeed or conclusively prove it's impossible. The exciting truth is that everything we've learned so far suggests success is achievable. Difficult, certainly. Expensive, absolutely. Requiring breakthroughs in multiple fields simultaneously, without question, but achievable. The final frontier. The race to 10 times light speed isn't just about science or engineering or national prestige. It's about whether humanity has a future among the stars or remains forever confined to this single planet, watching the cosmos from a distance we can never cross. That future is being written in laboratories right now. The next chapter of human history is taking shape one equation, one experiment, one breakthrough at a time. Harold White's team detected those nanoscale warp bubbles. Other teams are working on scaling up. Private companies are investing in research. International collaborations are forming despite geopolitical tensions. The pieces are moving into place. The physics appears to work. The engineering challenges, while severe, don't seem insurmountable. The energy requirements, while enormous, have dropped to potentially achievable levels. The timeline, while uncertain, keeps shortening as understanding improves. Nobody can guarantee success. The universe might yet have surprises waiting that make warp drives impossible despite our best efforts. Unknown physics might create insurmountable obstacles. Quantum effects might prevent scaling. Energy requirements might hit a flaw we can't overcome. These remain real possibilities. But betting against human ingenuity has historically been a losing proposition. We split the atom when it seemed impossible. We landed on the moon when it seemed impossible. We built computers that fit in our pockets when it seemed impossible. We photographed black holes when it seemed impossible. Warp drives seem impossible right now to most people, but to the researchers working on them, they seem merely very, very difficult. That distinction between impossible and merely very difficult represents the entire difference between humanity's future among the stars and humanity's confinement to Earth. The countdown has begun. Whether it takes 10 years, 30 years, or 50 years, someone will eventually generate a warp bubble large enough to encompass a spacecraft. Someone will eventually solve the energy generation problem. Someone will eventually build a vessel that can warp space-time around itself and travel faster than light. When that happens, everything changes. The galaxy opens, humanity's future transforms. We become what we've always dreamed of becoming, a civilization that reaches for the stars and actually touches them. The race to 10 times light speed is happening now. The finish line is out there somewhere, hidden in future years we haven't reached yet. But every day brings us closer. Every experiment provides new data. Every paper refines the theory. Every failed approach eliminates blind alleys and points toward productive paths. We're going to break the light speed barrier, not by violating physics, but by exploiting its deepest principles, not through impossible magic, but through possible engineering, not someday in the distant future, but potentially within the lifetimes of people alive today. The stars are waiting. The physics is sound, the race has begun, and humanity is finally learning how to run fast enough to win it. The universe built a prison around us with the speed of light as its bars, but it also left the key hidden in the equations of space-time itself. We're finding that key. We're learning to use it. And soon, maybe very soon, we're walking out of the prison and into the galaxy beyond. That's not science fiction. That's the future being built in laboratories today, and it's closer than you think.